Hi, this is Glenn Dane. I'm a professor in material science and engineering at The Ohio State University. And what I want to do today is tell you a little bit about work that we're doing to improve joining, primarily by making solid-state welds by collision, and we'll go on a few tangents. One thing I'm going to do this really at a very rapid pace. I think this makes for sort of the best web videos because you can go back, watch them, get references, all that, give you the high level, do it fast, won't waste your time. I want to acknowledge that there's a team of people, many of them shown here. Anupam Vivek is leading a lot of this work. Got some great graduate students, undergraduates who are helping me out. And then we have people that are sponsoring us. Department of Energy is great. The Alcoa Foundation has helped quite a bit. And ODSA and NSF are helping us with some commercialization activities right now. Here's the scheme. Right now, if you look at what's going on in automobiles, we want to use thinner sections of stronger materials. We like to use different sorts of materials in different locations. This allows us to make cars that are much lighter and to have great crash worthiness and great road performance, all of that. This creates a design problem. How do you stick these very thin, very strong materials together? How do you stick dissimilar materials together? And then really what you'd like is you'd like joints that are stronger than the components themselves. And I'm going to really try to summarize the state of the journey, and there'll be a few tangents here. Again, if you're seeing this online, there's lots of web resources you can entertain yourself with. So goal of what you'd really like is 100% joint efficiency. That means the joint is stronger than the base metal, and we can make a metric of the strength of the joint divided by the strength of the joint material. And if you hit 100%, that means you're going to break in the base metal, not in the joint, and that's what you'd like. Things are stronger that way, they're more predictable, and it liberates design. All of those things we see here. So how do we join things today? We usually use either fasteners or adhesives, are key ways of doing things. I'll talk more about them. Welds and brazes we can also use. These usually use high temperature. And there are fusion methods and solid state methods. And there are some other things. You could sew things together, snap fit, and we'll get back to that a little bit. I'm not going to go into great depth, but there's some slides that have a little more depth than what I'm going to give you here. So if you use fasteners, they work great. You can't quite hit 100% joint efficiency, but you can be very predictable, and they have various failure modes. You might shear through the fastener, you might shear the plate, you might tear across a row, and all of these things give you efficiencies of maybe 70% if you do it well. It's very predictable, but you also have to put a fastener in there. Fasteners add weight, they cost money, they might corrode, you might be able to get gook beneath them that causes corrosion. So fasteners are good, but they're not always awesome. Adhesives, again, they can be really, really good, but not always not awesome because, first of all, they're usually fairly weak, particularly in peel. With current conventional adhesives, it's hard to get peel strengths beyond about 100 pounds per inch. This is a weak mode for them. We're doing better by innovating adhesives, but they're still relatively weak. They do much better in shear, but again, you need very large sheared areas to get terribly high forces that are carried through them. There are other good reasons to use adhesives, however, because you can control corrosion, fatigue, you can control noise, vibration, and harshness, which that's an acronym for, and those are good sorts of things. The other thing you can do is you can weld metal, of course, and what we've been doing as metallurgists, or the metallurgical community, is making these microstructures very fine, very complex, and that gives them great strength, but then when you run a current through this and melt a region, it solidifies in a relatively uncontrolled way, and this welded region and the heat that's generated gives you fairly poor weld efficiency, both in shear and in peel. And here we plot joint efficiency as a function of material strength, and our materials are getting stronger and stronger, but as you get them stronger and stronger, you're doing more and more damage by melting them from a relative point of view. So if you start with mild steel, you'd have a 60% weld efficiency in shear, down here below 30%. If you have a peel test for your mild steel, you might be around 20% weld efficiency, and you're here around 5%. So as we get to stronger and stronger materials, even for simple monolithic systems, the joint efficiency really falls apart. So I'm going to talk mostly in this presentation about is joining, and there's a bunch of different ways of doing joining. I'm going to really talk about metallurgical joining. I'm going to talk about solid state because you have the promise of very high joint efficiencies. There are methods I will not talk about. I will not talk about friction, linear friction, friction stir, but I will talk about this area of impact using explosives, using electromagnetics, and using VFA, which stands for our Vaporizing Foil Actuator. I'm also going to talk about a method of doing interlocks, and this is what we call conformal joints, and that'll be the other thing that you'll see a little bit of presentation on here. So what we do in my group is we tend to use these methods that have very high speeds associated with them, and you can find references all over. If you put electromagnetic forming into the web, you'll find all sorts of stuff, and it works basically by putting a current around something, develops complicated magnetic fields, develops eddy currents, and that can cause this tube to crush in on itself at high speeds, up over 100 meters per second or so. We've also done some work on high-speed presses. You can see a publication we've done on that there. I'm going to talk a lot about this vaporizing foil actuator approach, which works nicely for sheet materials, sheet metals, up to several millimeters thick or a few millimeters thick. For very thin metal sheets, we can also do things with laser-driven flyers, and Hui Min Wong did some really nice work on that, and I refer you to her publications on our website at impulsemanufacturinglab.osu.edu if you'd like to see more on any of these. We've got a lot there. So here are our key processes we use, and we talked last about the process. Really want to talk about the advantages and things we can do. We can stretch material further this way. We can join things conformally. I'll show you this. Conformal collision welding I'll tell you about. The rest of this I'm not going to say much about. We can emboss, we can cut, we can do precision shape control, we can do agile flanging and hemming, we can also shock harden materials. I'm not going to say much about that, but what I will do is talk a little bit about light and agile equipment. What we can do is put forces on for millionths of a second, very, very high forces for millionths of a second, and that also allows you to use very lightweight equipment. I'll get to that in a moment. But first what I want to say is here are the foci that we're going to work on, look at here just a little bit. I'm going to talk a little bit about how we use electromagnetics to make conformal joints that look like this. These are examples of Boeing flies right now. Electromagnetics can also be used to make metallurgical joints. I refer you to like the BMAX website. Look at BMAX for electromagnetics. You can see some interesting things that they do. What I'm mostly going to talk about is this vaporizing metal approach. Again, we can use this for conformal joints down here. We can use this for this really cool process that Anupam Vivek developed. It's cool. We can use it for expanding tubes into plates. And of course, we can use it for welding. And that's what has been publicized a bit lately, and I'll talk about presently. So again, if you can put on forces really fast, force is the thing that really causes the action. It's the thing that really causes materials to flow or join or whatever. And it's the force or pressure that matters, not the time it's applied. So usually, we use big presses like this, and you might imagine we've got 200 tons we want to apply, and if you're going to do that and hold it for a large fraction of a second, you need a press. There's no real way of getting around that. But if you can find a way for putting this on for 5 millionths of a second, even if you've got a 50-pound fixture, that force, 200 tons of force over 5 microseconds, will only take a 50-pound plate and accelerate that to about a half a meter per second. There's lots of ways you can catch that. And so the inertia can hold things back if you can use very quick acceleration. If you've got something pretty small, though, for example, a 10 by 10 centimeter, 1 millimeter thick piece of aluminum, that's 27 grams, that same impulse, 200 tons for 5 microseconds, gives you about 350 meters per second of speed of that. That's enough to start doing welding and other interesting things. So you got to think differently. The world isn't static, and that's a big mindset difference with this. But going back, I mentioned we can use electromagnetics for conformal joints. Again, the key idea is what we do is take and have a tube, and we put a coil around the tube, run a very large current through the coil. That current develops a magnetic field, will cause eddy currents to flow in a ring, for example. Primary currents this way cause induced currents going that way. This can cause this ring to expand out at a couple hundred meters per second. Outward expansion we can use to lock things together like this, expand a tube from inside out to make neat locks. You can make things like interesting chairs here like that, and we've made some cool minimalist joints this way. We can also use it to lock an aluminum tube onto a steel yoke, and what's cool about that is we could also put a little layer of polycarbonate in between there, and then take the steel end and the aluminum tube, lock them together, and have no conductivity in between, so you avoid the ability to have any galvanic corrosion. So that works pretty cool. And again, acknowledgments to Andrew Sattler and Tony Lusher did this great demonstration. Again, it's a great way to put multi-material structures together, and unlike welding, get 100% joint efficiency. You have no ability for galvanic corrosion in this case, and there's also no distortion. It's a very cool way of putting things together. Boeing flies this regularly for torque tubes, but this is really, I think, a very underutilized technology. Another technology that's out there that's very cool that we are leveraging here is explosive welding. And there's been a lot of work that goes back to, I think, the 1940s and before, where basically you can take explosives, put them on top of a flyer sheet, cause the flyer sheet to move down at a speed on the order of 500 meters per second. If it hits at an appropriate angle and at the right speed, you get a jet to jet off the surface, and clean metal hits clean metal. Metals like to join with metals. That's not a problem so long as there's not an oxide in between, which there usually is. And you get these wavy interfaces. This is a nice example from Nobel-clad Dynamic Materials is the name they're formerly known as. They have a large cave in the middle of Pennsylvania where they do experiments like this, production like this on a daily basis, one shot a day, and they bond together literally acres of material. Typically it's stainless steel, which is expensive and has a lot of very precious elements in it, on top of carbon steel, which is relatively common, and you can bond them together and make these cool structures. But the problem is you need a big cave out in the middle of nowhere to do that. Before I talk about how else you can do this, when I talk about what you typically see with these welds, you see things going on at all kinds of scales, and this is a really nice example for a really nice analysis or explanation by Dirk Rabe's group out of Dusseldorf. And what they show is that all length scales going from macro to nano, you see interesting things. At the macro level, you see these waves. You see these waves have some structure. These waves have areas where they may have got real hot with eddy currents, and other areas that look very different. The structure here is very different than the structure here. And then if you take even one of these areas where it looks like it's a discrete interface, look in very closely, you see an area less than a micron, less than a millionth of a meter wide, where you see something different going on that is possibly some melting. It's possibly a mechanically alloyed region. One could argue about that, but there is something different that goes on there that has a different structure and may possibly be brittle. Here's some work from Yuan Zhang, who did a wonderful PhD thesis with me in 2010. Again, you see heterogeneities. These are areas where intermetallics form. You see areas where things look very discrete. Even where they look discrete, you look close up, and there's a region about 100 nanometers thick that has very refined grains that's possibly melting, possibly nanocrystalline region that's made by something like mechanically alloying. If you look at 6061 aluminum, this is where the interface is. You see large crystals down here. This is what the material looks like before you mess with it. When you get the two areas to slap together, you can see the grains get tremendously refined here, and that's another salient characteristic of the process. You get very fine grains. That means very high strength near the welded region, so you're actually increasing the strength in the welded region rather than decreasing it, which is kind of cool and very useful. Again, this gets us on this quest to joints that are stronger than what we're joining, which simplifies design tremendously. So the problem with doing these kinds of things, doing explosive welding, is not many people have an explosive range around. So we can't do this. If you do electromagnetic welding, it also, if you try to push things too hard, if they're too thick or too strong, you often destroy your coils. This is a flat coil from Sergei Golovashenko. He published that one. We've got lots of scrap like that also. And it's hard to get acceleration pressures greater than about 300 MPa, and that often limits you, depending on details of thickness and everything, up to speeds around 250 meters per second. It's really hard to use magnetic pulse to get 500-600 meters per second out of it, which is often the sweet spot for a lot of collision joining. So that was this idea for this vaporizing foil actuator approach that we'd like to say we invented from scratch. We, of course, didn't. There's very few things that are truly, truly new. But what we have done is this has been used for explosive detonation for years and years, and the exploding wire phenomenon has been used for years and years. And we're adapting this to manufacturing. We take a capacitor, charge it to a large voltage, run it through a switch. Any system has some inductance, some resistance. We use that then to blow up a bridge wire. And this is what it looks like when it happens. This is some cool pictures that we didn't do, that we pulled from the literature, that show what happens as you run electrons through a wire this way. This is the anode side. Electrons go from right to left, and you can see that the anode side is a little bit different than the cathode side, and there's also these interesting striations. But you see also this field that is very fast, that blows out, and it's much like an explosive pulse you get there. And we've done this, and others have also. You can see the pressure amplitude. Credit to a lot of other people coming past. The pressure amplitude you get out is huge. We can get gigapascals of pressure, an order of magnitude greater than you can get out of electromagnetics. And it depends on how much energy you can stuff in. So the metric that seems to be quite useful is basically this ratio of E over delta H sub B, where the small e is basically how much electrical energy you're able to stuff into the wire, and delta H sub B is how much energy it takes to sublimate that wire. So we can put twice as much energy it takes to basically vaporize the wire in, and that energy doesn't quite know what to do. It holds on, and then boom, it bursts, and that gives us very, very high pressures. So I'll go through a little bit more of that, but this is how this is used in welding. We basically take a piece of aluminum foil about 3/4 thousandths of an inch thick, put it in a polymer, run a current across it, and when we run this pulsed current across it, about 100,000 amps over a period of 5 or so millionths of a second, 5 or so microseconds, we turn that aluminum into vapor. That aluminum also likes to gather any oxygen nearby, which increases the flame temperature, would increase pressure. And we can use that to drive things. So just to be clear, if you're savvy in this area, this is not magnetic pulse welding. Magnetic part is sort of important, but not driving. We can get much higher pressures. This actually uses a lot less energy, which is cool. The figuration is very flexible, and this is robust. Everything that contains this is really just dumb steel, so we can do away with anything that's difficult. This is also not explosive welding. We can do this in a lab environment. This is reproducible at small volumes. Explosives don't work well at small volumes. No hazardous materials to store, and it's much, 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 much smaller energies. And we'll get to that at the end of this presentation. So we've published this in some depth, but this is really cool and really quite interesting. This is a complicated plot. This shows, in this case, current. This is the voltage shown there, and then this is the flyer speed. Flyer speed is shown here. Flyer velocity is shown here. So what we see happens is you see the current going up to, this is 100,000 amps in this case, and it rises and rises, and all of a sudden you're stuffing all of this energy, heating this foil electrically. All of a sudden it can't take it anymore. It starts to burst. The current drops off. You can see as the current drops off, the voltage peaks. And the flyer, which is starting to be electromagnetically accelerated a little bit, and we've got great instrumentation to do this. We've invested heavily in time and money in a technique called photon Doppler velocimetry that allows us to measure flyer velocity as a function of time or distance traveled. You can see we go here from about 50 meters per second to over about 10 millionths of a second. We're up here close to a kilometer per second. Massive rates of acceleration. From that, we can figure out what these pressures are also. That's how it works. You're stuffing electrical energy in. All of a sudden, the foil says, I can't take it anymore. And boom, it turns into vapor. This is how we use this as a welding process. We've got this photon Doppler velocimeter in here, so we can measure the speed. And you can see the material comes up here. It strikes here first, it strikes normal here, and then as you get out to the side, you strike at an angle, And where you strike at an angle, you can see a weld region. So this is what an aluminum to magnesium weld made like this looks like in plan view. If you peel it apart, an aluminum to magnesium don't make super tough welds, other systems do. You can see this is the welded zone. This is this sort of racetrack zone here is where you have a weld. And in the center where you see normal collision, it doesn't weld, but over this region you get the right combination of angle and speed, and you see that weld region there, and that's what we try to optimize. And there's lots of ways of modifying this geometry, and we're working on multiple ways of modifying the geometry so you can maximize the strength configuration and so forth. What's really cool is this works for a large number of materials, and the thing that's the most critical thing we think is if you take these materials after you join it here, if you basically can take this thing, which we call the flyer, and try to peel it off this thing that we call the target, and if you try to peel them, we see great disparity in how things work. Like I say, magnesium, this is a magnesium alloy to aluminum, gives you relatively poor peel strengths that we measure as you see down there. But most other materials, many other systems will fail in the base metals. That means you get 100% joint efficiency. All of these that you see here basically failed in the base material. And most of these it's copper, but which isn't terribly strong, but it fails there, and I'll show you some other systems where it does also. So, and that's one of the things that's very scientifically interesting is understanding which materials you get strong bonds with, which ones you get poor bonds with, and we're working on that right now. And then the other thing that's interesting from a practical point of view is what kind of geometries can we use. So there are other interesting systems we're working on that show great promise. We're still working on magnesium to aluminum. We're making that work, working on it. This is modest strength steel to aluminum. That works well. Very high strength steels to aluminum also work well. This will generally fail in the aluminum, not at the interface. This is a high strength but not super high strength material to aluminum. Also works quite nicely. The system that routinely makes the most beautiful interfaces is that of the copper tungsten weld, and we've got a nice publication on this. We did a cool study, I think it's cool anyway, I'm biased, where we made targets that have various collision angles associated with them, and then we put different collision speeds into this, and we could fairly quickly, with different experiments, each one of these at a different speed represents a different experiment. Targets have different angles in them, and you could see what the interfaces look like. And you see some here at high speed and low angle. These tend to melt, not work so well. Lower speeds, you tend not to really close everything up. But there's sort of this Goldilocks region in here where things are pretty much just right, and you get these remarkably cool wavy interfaces that develop also. So that's a method that you can use to figure out where the sweet spot is. And we can plot this as a function of impact velocity versus collision angle. We see areas where there's melting, areas where there's voids, areas where things are wavy, and you can see all of that here. And again, there's also ways we can look at this with respect to peel strength. We do a lot of work like this, and we're also concerned about the places where we have weak peel strengths. Another system that tends not to be real tough, that's one of great commercial interest, is titanium to steel. And you can see pretty much no matter what we've done so far, we get these interfaces that don't look that pretty and they're cracked up, and we don't understand all of that yet, but we can create them and see what they look like. But we can also modify them, and before I modify them, let me show what they look like. When we peel them, you can see despite them having relatively poor peel strength, and again, your better adhesives are up here between about 10 and 15 newtons per millimeter. So this is, not terrible, but it's not awesome either. But if you peel them, we can use energy dispersive spectroscopy and a scanning electron microscope, and we can look at the images on the titanium and the iron side, and we can also light up the green atoms as iron and red atoms as titanium with the electron optics that we have. And you can see there's considerable material transfer on both sides after this, so we are getting real metallurgical joining between the two. If we want to make it stronger, turns out what we can do is we can put a layer of nickel in there and have this hanging in between the titanium and the steel, and it'll bond to both sides. It doesn't look completely awesome, but it does well enough. And then what this does is it actually is strong enough that it gives you 100% joint efficiency and pushes the failure into the titanium, making the joint stronger than the weaker of the two materials. So these interlayers are a very powerful way of taking some of these things that are challenging for us now and giving us very strong interfaces. The other thing you can do with this is a more complicated one, and this is in Welding Journal as of recently also. We can do multiple layers where we can also take titanium and bond it to steel and put multiple layers. In this case, we've got niobium and copper here, and this makes for a system where you will not have reaction between the steel and titanium that's deleterious, and that holds together nicely and gives you a system where you could even imagine heat treating or carburizing the steel without adversely affecting the titanium, which is cool. And again, I'll point you to the paper for more details. The other thing we're just working on now, and we have a great collaboration with Brad Kinsey, Ali Nassari, and Brad's team at University of New Hampshire, where we're doing experiments. He's working on simulations. This is working well. We use a couple different techniques. Smooth particle hydrocode can tell us that we should expect jetting. The ALE of arbitrary Lagrangian Eulerian approach lets us see that we also can get waves in here. The waves look something like what we see in the experiments, which is cool. And the other thing that's really cool is their approach can also tell us what the temperatures should be. This is an example where at a collision of about 340 meters per second, we see temperatures expected around 400 degrees C at the interface, whereas if we get too hot, 540 degrees C at the resolution of their mesh, we see high temperatures there, up over 700 degrees C. That causes melting, and that seems to be confirmed that we have fairly significant melting when we do the scanning electron microscopy on this. So we just have a beginning NSF program in collaboration with Professor Kinsey and his group, and we're excited about that. Okay, where does this go? This is, to me, the most interesting and fun part of all of this right now is how do we get this out into the world? And we're working with a program through the National Science Foundation called I-Core to do this. And I-Core, what they really want you to do is not build an expensive prototype that nobody might need, but instead go out and talk to a bunch of people, see if you can do 100 interviews with thought leaders, people who use the technique, and we've done that. Anupam Vivek led that. And we came up with a bunch of conclusions, things that people would really like. They'd like higher joint efficiencies, that's clear. They'd like to see steel to aluminum joining, that's clear. They'd like to see us join unweldable materials like 7000 series aluminum to itself, and Apple's all about 7000 aluminum right now. You see that in the new iPhones and watches and so forth, and it's very strong, hard to weld, traditionally unweldable. And then really importantly is we need to develop solutions that play well within existing manufacturing infrastructure. We got to make this friendly, and that's what we're really working on right now. So a couple of ways of making this friendly. At fairly modest energies, 10 kilojoules, which isn't a whole lot for pulse power. We can do some other things which are interesting. One is we can take and drill some recesses in a target plate, use something that's a flyer. It doesn't really fly, it doesn't move much, use a foil actuator to develop very high pressures, squeeze that material into those recesses. This is an example of T6, full hard 6061 aluminum, pushed into these recesses in steel. We actually see very good strengths out of this, and these things are also aesthetically gorgeous. It's a beautiful way to put things together. Gives you very high strengths, and you don't see any ugly weld spatter or uncontrolled deformation. Really cool. That's something we think is useful for commercialization. The other thing that is useful for commercialization is we're starting to work with the topology. We need some standoff, but we can use a bit of urethane for a standoff. The urethane ends up getting spit out. We end up with a nice traditional spot weld or lap weld instead of this. We can also do spot welds. We use a gasket that goes around this, and again we can join steel to aluminum. The gasket is also included in there. It's deformable, but that also protects that region of this interface from galvanic corrosion right there. There's still an electrical contact, but the area where the interface comes to that can be protected by this interface, and this foil that we makes for a great way of focusing the energy. We can also use this very focused foil to do something like this, where we take a fire, put some shape into it, bang it back against the target, and we end up with welds that look like this. Again, they're very pretty, and they're also very, very strong. And the other thing is we get very high efficiencies with this spot weld approach. And I'll talk more about efficiencies in a second, but the other thing I'll emphasize again is because this is a fusion weld, is not a fusion weld, because it's a solid state weld, we plot hardness versus distance from interface. We don't see a weakened zone. If anything, you see zones near the interfaces that are hardened. And again, this puts material, puts the failure back into the weaker of the two, and the weaker of the two materials in the pair, giving you 100% joint efficiency. Here, these are examples of these kind of patch welds pulled apart. They fail in the base materials. If we make a spot weld, it also fails in the base material. So the most interesting thing we're doing lately is we've been working on efficiency. We've been trying to really downsize this. We've created something that looks like a spot welding head that looks like that, uses very small foils, uses a capacitor bank like this we can build ourselves. This has a very fast rise time associated with it. When we use the small foils, the fast rise time bank, we only need about 1.2 kilojoules of energy to make that weld. And we've done it under 1, and we can make very nice welds, and the shear strengths are roughly twice of the shear strengths of other welds we see in the literature. The other thing that's cool about this is the energy is really low. We're using about 20% of the energy that's used in resistance spot welding to do this. And we end up getting better properties along the way. So we are pretty confident we'll be able to do this at about 1 weld per second. If we can do 1 weld per second at about 1 kilojoule per weld, and we think we can, that's a 1 kilowatt kind of thing. This spot welding system is using about as much energy as a microwave oven typically would. It's very efficient in terms of how industrial equipment works. Great energy savings in the plant. And again, you're getting basically 100% shear, 100% joint efficiency there. So this is where we see this going, as we see a little system that would end up feeding foils through. This is the foils that are on this. This is a little bit of a backing, and we think this can replace basically spot welders. It's a completely different way of doing things. We can join steel to steel, aluminum to aluminum, 7000 series aluminum to itself, 7000 series aluminum to steels, and all works with the same piece of equipment, which is kind of cool. This is what we're current project we're working on right now. So again, just to kind of summarize, I started with the idea of joint efficiency, and we're showing 2 practical approaches how we get high joint efficiencies. One is with this conformal joining, which is basically ready to go. The other one that we're working on is doing impact welding, and kind of the low-hanging fruit there is really doing high-strength aluminum alloys to themselves without heat-affected zones. Here's 6022 in the T4 condition, common automotive alloy spot welded to itself, and you can see this weld is stronger than the base material, much stronger than you would see with a typical weld where you'd melt things. So I'm going to stop there, just close out. Joining is a problem. Fusion welds are bad because of the metallurgy. It's not good to melt things. Adhesives are mediocre. Fasteners are better than adhesives most of the time, but have their drawbacks. Solid state welding is really a great way of doing things because you don't melt materials. It's a fairly different way of doing things, and we're now getting very low energies for this, very high versatility, very high joining efficiency, high strengths. We can put dissimilar materials together, no heat affected zones. The process can be automated. See our website for a lot more details. Links to our publications are there. And thanks so much to my great research team and the sponsors. Department of Energy presently right now is helping us with a lot of this work. That's it. Please feel free to feel free to hit me on the web with any questions that you might have. Thank you, and take care. Bye.